Hello, in this session I'd like to talk about integral, which is getting an area of a graph. So if there is a graph f of x that looks like this, and I would like to get an area between x equals to a and x equals to b, then the area is simply the integral from a to b of f of x times dx. What this means is that I'm gonna slice this into infinitesimal pieces, in which this infinitesimal area, I'm gonna call it dA, equals to f of x times dx, in which dx is the infinitesimal increment here. And this integral, you can kind of think of it as the sigma or like the summation form, in which since dx is infinitesimal, this sigma became this elongated like integral sign. And the fundamental theorem of calculus, this is probably the most important theorem for learning calculus, is that if big F prime of x equals to f of x, then the integration of f of x dx from a to b equals to big F of b minus big F of a. And in general form, the integral of f of x dx is big F of x plus some constant c. Now there is this constant c that is attached, because if you take a derivative of big F of x, then since this constant term becomes 0, any solution in this form would have a derivative resulting in f of x. Therefore, you have to attach the c at the end if you're taking this like general integral without a bound. So let's do an example. Integration of x from 1 to 2. Now, the function x equals to 1/2 times derivative of x squared, because derivative of x squared equals 2x, and a 2 would be cancelled out with this 1/2. And similar to derivative, I can take out the constant for integration. So this equals 1/2 times the integral from 1 to 2, derivative of x squared prime, derivative of x squared dx. And using fundamental theorem of calculus, this becomes 1/2 x squared from 1 to 2. Now this denotation of a line means you put this value at the top and subtract it with the value at the bottom, in which it will be 1/2 2 squared minus 1/2 1 squared, which is 3/2. Now to verify my integration, my integral would be getting an area of f of x equals to x from 1 to 2. Now this is a parallelogram of base 1 and 2 with height 1. So the area would be 1 plus 2 divided by 2 times height, which is 1, which would be 3/2, which again, this result in which we geometrically calculated the area matches with the integral that we have done. Now there are several techniques of integration, as integration is much harder than taking derivatives, and you have to develop intuition on integrating a function based on lots of practice. So the first one is integration by parts. Remember from product rule, derivative of u of x times v of x is in the form of u prime of x times v of x plus u of x times v prime of x, in which if I solve for u prime v, then u prime v equals to derivative of u times v minus u times v prime. Now if I take the integral of this whole expression, then the integral of u prime v dx equals to, integration of this is just simply u times v plus some constant c minus the integral of u times v prime dx. Now the use of this is for a function such as integral of natural log x. In this case, I'm going to say u prime equals to 1 and v equals to natural log of x. Now, in this case, u of x would become x, because if you take the derivative of x, this becomes 1. Now, in terms of u's and v's, you don't have to worry about the constant c's. It would still work out. And for v prime, the derivative of natural log of x is simply 1 over x. So therefore, the integral of natural log dx would be u times v, which is x natural log times x, minus the integral of uv prime, which is x times 1 over x dx, and this cancels out to become 1, and this expression becomes x ln x minus x plus some constant c. Now let's verify this result that we got from integration by parts. So taking the derivative of x ln x minus x plus c, this becomes natural log of x plus x times 1 over x from product rule. This becomes negative 1, and that becomes 0. Now notice how this term, the x cancels out to become 1, and the 1 cancels out to negative 1, and becomes natural log of x. And therefore, from fundamental theorem of calculus, our result from the integration by parts is correct. So the second technique is called u substitution, and the definition of u substitution is integral of y of u of x times du dx dx equal to integral of y of u du. Now what this means is that, for example, if I'm integrating e to the 2x squared plus 3 times x dx, then I see that this e to the 2x squared plus 3 expression is a function of 2x squared plus 3. So therefore, I'm going to set u as 2x squared plus 3, in which u prime becomes 4x. And this expression, this equals the integral of 1/4 times 4x times e to the 2x squared plus 3 dx. And if I plug in these values, this becomes 1/4 times integral of e to the u times du dx times dx. Now, in this case, you can quote-unquote cancel out the dx, and becomes 1/4 and times the integral of e to the u du, in which this becomes 1/4 times e to the u plus some constant c. So in pre-calculus, we've learned polar functions as a form of r of theta. So for example, r of theta equals to cosine theta looks something like this. Looks like a circle that has been shifted by the distance 0.5. Then the area of this polar curve equals to the integral from theta initial to theta final of 1/2 r squared d theta. And the proof of this is that for some generic polar function that looks like this, the infinitesimal area that is bounded by infinitesimal angle of d theta equals to 1/2 r squared d theta. And this is because for a circle with radius r, the area equals to pi r squared, which in this case equals to 1/2 times r squared times 2 pi, in which the quote-unquote angle of this circle equals to 2 pi. Therefore, for any arc with radius r and angle theta, the area equals 1/2 r squared theta. So therefore, for this infinitesimal area, we can approximate that this length equals to that length. So therefore, this area is an arc with angle d theta. Therefore, area of this infinitesimal piece can be approximated as 1/2 r squared d theta. Therefore, the total area, which is the integral of dA, is simply integral of 1/2 r squared d theta. So for example, if I want to get an area of the curve r equals cosine theta, then the area equals to 1/2 times the integral of 0 to pi of cosine squared theta with respect to theta. And reason that the integration bound is from 0 to pi is that initially when theta equals 0, the position of the polar curve is here. And when theta equals pi, when this is facing that direction, cosine of pi equals -1, which means negative of this negative x direction is positive x direction. So therefore, for this full cycle, the integration bound is from 0 to pi. In evaluating this integral, remember that cosine of 2 theta equals to cosine squared theta minus sine squared theta from trig identities. And if I subtract cosine squared theta and add cosine squared theta, these two terms becomes 2 cosine squared theta, and this term is simply negative 1. But since I've subtracted and added the same value, this cosine 2 theta equals to 2 cosine squared theta minus 1. Therefore, cosine squared theta equals to 1 plus cosine 2 theta divided by 2. Therefore, 1/2 the integral of cosine squared theta d theta equals to 1/2 the integral of 1 plus cosine 2 theta over 2 d theta, in which this is 1/2 times 1/2 theta plus 1/4 sine of 2 theta from 0 to pi. And since sine of 0 and sine of 2 pi has the same value, this value disappears and the value of integration becomes pi over 4.